first things first, I am not as studied on the next couple chapters as I am on everything else on the book. It is something that I didn't learn in undergrad, but I have been teaching this class for long enough that I have a pretty good understanding of it just from the conceptual level. However, as I am not an authority on it, I am going to let the book take lead, and a lot of this is just going to be verbatim. That said, let's move on to chapter 33, the atomic nucleus and radioactivity. The first thing we want to talk about are X-rays. So deeper probing into the atom began in 1895 when the German physicist Wilhelm Röntgen discovered X-rays, rays of an unknown nature. Röntgen discovered his new kind of rays produced by a beam of cathode rays, later found to be electrons striking the glass surface of a gas discharge tube. He found that X-rays could pass through solid materials, could ionize the air, showed no refraction in gas, and were undeflected by magnetic fields. Today we know that X-rays are high-frequency electromagnetic waves, usually emitted by the de-excitation of the innermost orbital electrons of atoms. Whereas the electron current in a fluorescent lamp excites the outer electrons of atoms and produces ultraviolet and visible photons. More energetic beam of electrons strikes a solid frequency, excites the innermost electrons, and produces higher frequency photons and X radiation. X-ray photons have high energy and can penetrate many layers of atoms before being absorbed or scattered. X-rays do this when they pass through your soft tissue to produce an image of the bones inside your body, figure 33.1 on the right. In a modern X-ray tube, the target of the electron beam is a metal plate rather than the glass tube or wall. More than 99.9% of the atoms in our everyday environment are stable. The nuclei in those atoms will be unlikely to change over the lifetime of the universe. But some kinds of atoms are unstable. All elements that have an atomic number greater than 82, lead, are radioactive. These elements and others emit three distinct types of radiation named after the first three letters of the Greek alphabet: A, B, G, alpha, beta, and gamma. Alpha rays have a positive electric charge, beta rays have a negative electric charge, and gamma rays have no charge at all. The three rays can be separated by placing a magnetic field across their paths. Further investigation has shown that an alpha ray is a stream of helium nuclei and a beta ray is a stream of electrons. Hence, we often call these alpha particles and beta particles. A gamma ray is electromagnetic radiation, a stream of photons whose frequency is even higher than that of X-rays, whereas X-rays originate in the electron cloud outside the atomic nucleus. Alpha, beta, and gamma rays originate in the nucleus. This is why they are called nuclear radiation. So, just as light is emitted by energy level transitions in atoms, gamma rays are emitted by similar energies transitions within the atomic nucleus. Gamma photons provide information about nuclear structure, much as visible and X-ray photons provide information about electron structure. While we might think that radiation is a new idea, what actually accounts for most radiation is natural background radiation for 75% of the radiation, with 8% just being food and water. Radiation dosage is commonly measured in rads. Radiation absorbed dose, a unit of absorbed energy. One rad is equal to 0.01 joules of radiant energy absorbed per kilogram of tissue. The capacity for nuclear radiation to cause damage is not just a function of its energy level, however. Some forms of radiation are more harmful than others. For example, suppose you have two arrows, one with a pointed tip and one with a suction cup at its end. However, shoot both arrows at an apple at the same speed and both have the same kinetic energy. The one with the pointed tip, however, will invariably do more damage to the apple than the one with the suction cup. Similarly, some forms of radiation cause greater harms than other forms when we receive the same number of rads from both forms. The unit of measure for radiation dosage based on potential damage is the REM, Röntgen equivalent man. In calculating the dosage in REMs, we multiply the number of rads by a factor that corresponds to different health effects of different types of radiation determined by clinical studies. For example, one rad of alpha particles has the same biological effect of 10 rads of beta particles. We call both of these dosages 10 REMs. Lethal doses of radiation begin at 500 rems for a whole body dose. A person has about a 50% of chance of surviving a dose of this magnitude delivered to the whole body over a short period of time, such as a day or less. During radiation therapy, a patient may receive localized doses in excess of 200 rems each day for a period of weeks. All the radiation we receive from natural sources and from diagnostic medical procedures is only a fraction of 1 rem per year. And then here you can see the radiation exposure in millirems. And if you look at it, air is the highest dosage of millirems at about zero point 0.2 rems, whereas all of them added together are, as the book said, less than one. In scientific laboratories, radioactive samples of all the elements have been made. This is accomplished by bombardment with neutrons or other particles. Radioactive materials are extremely useful in scientific research and industry. To check the action of a fertilizer, for example, researchers combine a small amount of radioactive material with the fertilizer and then apply the combination to a few plants. The amount of radioactive fertilizer taken up by the plants can be easily measured with radiation detectors. From such measurements, scientists can inform farmers of the proper amount of fertilizer to use. The atomic nucleus occupies only a few quadrillionths of the volume of the atom, leaving most of the atom as empty space. The nucleus is composed of nucleons, which is the collective name for protons and neutrons. Each nucleon is composed of three smaller particles called quarks, believed to be fundamental, not made of smaller parts in the same way that an electron is fundamental. Just as there are energy levels for the orbital electrons of an atom, there are energy levels within the nucleus. Whereas orbiting electrons emit photons when they make transitions to lower orbits, similar changes of energy states in radioactive nuclei result in the emission of gamma ray photons. This is gamma radiation. We know that electric charges of like signs repel each other, so how is it possible that positively charged particle protons in the nucleus stay clumped together? This question led to the discovery of an attraction called the strong force, which acts between all nucleons. This force is very strong, but only over extremely short distances, about 10 to the negative 15th meters, and the approximate diameter of a proton or neutron. Repulsive electrical interactions, on the other hand, are relatively long range. A comparison of the strengths of these two forces over distance for protons that are close together, as in small nuclei, the attractive strong force easily overcomes the repulsive electric force, but for protons that are far apart, like those on opposite ends of a large nucleus, the attractive forces may be weaker than the repulsive electrical force. A large nucleus is not as stable as a small one. In a helium nucleus, for example, each of the two protons feels the repulsive effect of the other. In a uranium nucleus, each of the 92 protons feels the repulsive effect of the other 91 protons. The nucleus is unstable. We see that there is a limit to the size of atomic nucleuses. For this reason that stable isotopes of larger atoms have increasingly more neutrons in their nuclei than protons, and all nuclei that have more than 82 protons are radioactive. The more protons there are in a nucleus, the more neutrons are needed to help balance the repulsive electrical forces. For light elements, it is sufficient to have about as many neutrons as protons. The most common isotope of carbon, C12, for example, has equal numbers of each, 6 protons and 6 neutrons. For large nuclei, more neutrons than protons are needed. Because the strong force diminishes rapidly over distance, nucleons must be practically touching in order for the strong force to be effective. Nucleons on opposite sides of a large atomic nucleus are not as attracted to one another. The electrical force, however, does not diminish by much across the diameter of a large nucleus, and so begins to win out over the strong force. To compensate for the weakening of the strong force across the diameter of the nucleus, large nuclei have more protons than neutrons. Lead, for example, has about 1.5 times as many neutrons as protons. So we see that neutrons are stabilizing and large nuclei require an abundance of them, up to a point beyond which not even neutrons can hold a nucleus together. Interestingly, neutrons are not stable when they are by themselves. A lone neutron is radioactive and spontaneously transforms into a proton and an electron. A neutron needs protons around to keep this from happening. The alpha particles emitted in alpha decay are literally nuclear chunks, and only heavy nuclei emit them. Beta and gamma particles, on the other hand, can be emitted by radioactive nuclei, both heavy and light. In A, you see alpha decay, where a neutron decays into a proton and electron, where the positively charged proton and the negatively charged electron being near each other or being produced by the neutron means that overall the charge of the universe is not affected by this. I will also note that this is caused by the weak nuclear force, which is the last of our four forces that we have in physics: gravity, electromagnetic force, the strong nuclear force, and the weak nuclear force. In beta decay, a new proton is formed from a neutron, which occurs when not enough protons are around to stabilize the neutron, which occurs in a heavier nuclei, as there are more neutrons than there are protons in those. An electron is ejected, and then an alpha particle, which is two protons and two neutrons, is ejected after that. The change in the number of undecayed atoms is dependent on the number of atoms that there are to decay in the first place. This gives rise to a decreasing exponential curve like you see in the graph. The half-life is then defined as the amount of time that it takes for half of the remaining atoms to decay or the remaining nuclei to decay. So if you have a half-life of 1,620 years, then 1 kilogram of an object will become half of a kilogram of a material over 1,620 years. Over the next 3,240 years, it's only going to be half of that half because the amount that decays is dependent on the amount of a material that there is. And then this leaves us with a quarter of the original material. And then after 4,860 years, which is the third time, you have half of that quarter. So you have 1/8 of the original material over three half-lives. An interesting thing about this decay is it actually changes the element that uh, atom or nuclei is. So consider uranium-238, the nucleus of which contains 92 protons and 146 neutrons. When an alpha particle is ejected, the nucleus loses two protons and two neutrons. Because an element is defined by the number of protons in its nucleus, the 90 protons and 144 neutrons left behind are no longer identified as being uranium. What we have is the nucleus of a different element, thorium. This transmutation can be written as a nuclear equation where the uranium-238 becomes thorium-234 plus helium-4. Thorium-234, the product of this reaction, is also radioactive. When it decays, it emits a beta particle. Since a beta particle is an electron and this beta decay also creates a proton. The atomic number of the resulting nucleus is increased by 1. So after beta emission by thorium with 90 protons, the resulting element has 91 protons. It is no longer thorium, but the element protactinium. Although the atomic nucleus has increased by 1 in this process, the mass number, protons 1, neutrons, remains the same. The nuclear equation is thorium-234 goes to protactinium-234 plus 1 electron. Doing this, you can have different atomic numbers with different numbers of atomic mass by alpha decaying and beta decaying. You can lose protons and you can gain protons. This means that these isotopes have different numbers of atomic mass even though they are the same overall element. Finally, we're going to talk about carbon dating, which is a very practical application of this nuclear decay. So, carbon-14 is a radioactive element, but plants, as they're alive, take in carbon dioxide as long as they live, and the carbon 14 lost by decay is immediately replenished by fresh carbon 14 from the atmosphere. In this way, a radioactive equilibrium is reached where there is a constant ratio of about one carbon 14 atom to every trillion carbon-12 atoms. When the plant dies, however, replenishment of carbon-14 stops. Then the percentage of carbon-14 decreases at a constant rate given by its half-life. The longer a plant or other organism is dead, therefore, the less carbon-14 it contains relative to the constant amount of carbon-12. The half-life of carbon-14 is about 5,730 years. This means that half the carbon-14 atoms that are now present in a plant or animal that dies today will decay in the next 5,730 years. Half of the remaining carbon-14 atoms will then decay in the following 5,730 years, and so forth. Using this decay rate, we can tell how old something is by how much carbon-14 it has compared to the carbon-12 in the system.